Hello, fellow problem solvers. So they're going to be doing a problem that's a sort of introductory geometry problem where you can practice your skills. And it's a sort of theorem that you can use in other problems. Namely, we're going to be talking about the Feuerbach or the 9-point or the Euler circle in geometry. And the problem is this. You have a triangle ABC and let H be the orthocenter. Let A1, B1, C1, A3, B3, C3 be the midpoints of BCCA, AB, AH, BH, CH, respectively. Let the intersections between these heights and the opposite sides be A2, B2, C, A2, B2, and C2. And finally, you need to prove that all these points, A1, A2, A3, B1, B2, B3, C1, C2, C3, lie on the same circle, and that the center of that circle is the midpoint of OH, where O is the circumcenter of the triangle ABC. So you need to prove that these 9 points all lie on the same circle. Now, I would invite you to pause for a minimum of 10 minutes and figure out what the next steps should be. Like, how would you even begin proving this? What would your approach be? But if you want to try it all by yourself, a minimum of 15 minutes, ideally 45 minutes to an hour, hour and a half, not more than 2.5 hours. It's a nice little thing where you can practice your angle chasing skills. So now without further ado, let's begin. So the first sort of thing is that we don't really need to look at all 9 points. If you think about it, we can say to prove 9 points on the same circle, it's enough to pick 3 points and then prove that every one of the other 6 points lies on that circle, right? That is enough, sort of. You can then figure out, it has one center and stuff like that. You could also figure out, take the midpoint of OH, call that point N, and then calculate the distances from N to A2 and A1, from N to B1 and B2, prove that all these distances are the same. And that's one approach. The approach I like to take, the one I think is the most natural, is to pick 3 points here and then prove that some other points lie on the same circle as these other 3. And I invite you to take 5 minutes and think, which 3 points would you pick? It really depends what your style is, but think about which 3 points would you pick and what would you need to prove. Take 5 minutes now. And here are the 5 points that I would pick. The 3 points I would pick would be, really for me, it would have to be, I would say A2, B2, and C2. And why is that? Why would I not pick, say, A1, A2, A3? Well, if I picked A1, A2, A3, I could do that. But I'm thinking, hey, if I pick those 3 points, then I need to prove that C3 lies on the circle. And then by analogy, I have B3. And I need to prove C2 and C1. I need to prove that 3 other points lie on that circle. Versus if I pick A2, B2, C2, I only need to really prove that A1 and A3 lie on that circle. Because if A1 lies on that circle, then we have that B1 and C1 also lie on that circle. And if A3 lies on that circle, then we have 2 other points. So that's sort of the thinking why I would choose these 3 points. I mean, you could also choose the midpoints. You could choose these, any triplets of AI, BI, CI. You could choose them. I just feel with these, I have something more tangible to start off with. So now we have 2 things we need to do. One, prove that A1 lies on this circle. And the second thing is prove that A3 lies in that circle. Now, I'm going to begin with A3 and then move on to A1 just because I can use this picture right now and I immediately see a proof for A3. And I invite you to pause for 10 minutes and try to push the problem further, prove it yourself. And here's the next step. So let's label this as alpha, beta, gamma. Now what do we have? This is 90, so this whole thing is 180. But we also have, because this angle is gamma, we know that this angle is 90 minus gamma. We know that this one is 90 minus beta. And now we also know this is 90 minus alpha, 90 minus alpha, 90 minus beta, and 90 minus gamma. So what do I want? Well, I want to prove that, say, A1 is, actually, let me go with A3 first. I want to prove that A3 is on the circumcircle with of A2, B2, C2. Okay, what is the easiest way for me to do this? Well, the easiest way for me to do this is to calculate this angle right here and prove that this angle right here is equal to this angle right here. That's about it. Now, what is the angle A2, C2, B2 equal to? Right? How do we get this angle? I invite you to pause for 5 minutes and figure out how would you get this angle. And here's the next step. You would get this angle by saying, okay, wait, this is equal to the sum of these two angles, right? This is equal to the angle A2C2H plus the angle B2C2H. Now, what do I know? I know this is 90 and this whole thing is 90. So these 4 points are concyclic, which means I know that A2C2H is equal to what? Is equal to this one, A2BH. So this is equal to A2BH. And then this is equal to B2AH. B2AH. And when you have this sort of symmetry, you see A2, B2, BAH, it sort of tells you that you're on the right track. Now, what is this equal to? Well, this is equal to this angle plus this angle. This is 90 minus gamma plus 90 minus gamma. This is equal to 180 minus 2 gamma. And it checks out. Like you'll have 180 minus 2 gamma, and then you expect by sort of analogy this to be 180 minus 2 beta and 180 minus 2 alpha. And when you check the numbers, it works out. So what is this angle? We need to prove that this angle right here is equal to 180 minus 2 gamma. Now, let's solve the problem backwards. What would that mean? If this angle was 180 minus 2 gamma, what would that give us? Take 2 minutes to figure that out. What would that give us here? Well, the answer is, because this is 90 minus gamma, this would be half of this angle. So that would mean that this angle is also 90 minus gamma, which would mean that B2A3 is equal to A3A, which we know is equal to A3H. What does this remind you of? This means that we have a right triangle, and we do. So now let's solve the problem forwards. We have, because this is a right triangle, HB2A is a right triangle, A3 is the midpoint of the hypotenuse, then we know that A3A, A3H, and A3B2 are the same, which means this angle right here is 90 minus gamma. It's equal to this angle right here, which means this angle is 180 minus 2 gamma. And with that, we have shown that this angle is equal to this angle. And so we have that these 4 points are concyclic. In other words, we have from here, this is equal to the angle A2, A3, B2. And now from here, because this is equal to this, we have that A3 is also part of the circumcircle around A2, B2, C2. Now that we have this, I invite you to pause for 10 minutes and figure out how we're going to do A1. And now I'll clear up the picture. Okay, so now what do we have here? We need to prove that A1 is also on the circumcircle around A2, B2, and C2. Because once we got A3, we got B3, and we got, what was the other one? Yeah, C3. So what do we need to do here? Well, we know this is the midpoint of BC. Let's see, we know that from the similar calculations we had before, this angle is equal to this one. Like this whole thing, C2, A2, B2 is equal to 180 minus 2 times alpha. All right, so now with that, we need to prove that this angle right here is equal to 180 minus 2 alpha, right? So how do we do this? There are many ways to go about doing this. Now, one way is to say, wait a second, what do I know? I think this is actually, I'll first show, like there's the angle chasing way. You can literally chase all the angles, do a similar thing we did before with because you have a right triangle here, a right triangle here. You can calculate all the angles pretty much. But I want to show you a different sort of thinking, a way of to think about this. Is you have this is 90 minus alpha, right? And so is this. In fact, the points B, C2, B2, and C lie on the same circle. Now, what is the center of that circle? Well, because this angle is 90 and this angle is 90, this means that the center of the circle is the midpoint of BC. Oh, that's A1. Now, what do we know? We know that in any triangle, that the angle, if you have this is the center, if this is some chord x, y, this is z, we know that the angle XOY is equal to twice the angle XZY. You can prove this just, again, by angle chasing, because you have this is equal to this, and this is equal to this, and this plus this plus this plus this is equal to this, which gives you this is 2 times z. That's a quick proof. But using that, and it's a fact that you can generally cite, and just using that fact, you can say, because this is 90 minus alpha, this must be twice 90 minus alpha, so this is 180 minus 2 alpha. We know this is 180 minus 2 alpha. And so we are done. We've proved that A1 is also part of this circle around A2, B2, C2. And with that, let's move on to our next point, which is proving that O, the midpoint, actually not the midpoint, the circumcenter of ABC, if we take OH and we take their midpoint, call this point N, that this point is the center of this circle. So how would we go about proving that? I invite you to take 5 minutes and figure out how would you prove this fact. And here's the answer. So what do we know about the center of this circumcircle? Well, it has to lie on the intersections of the side bisectors, right? This is the center. It's on the intersection of the side bisector of xy, yz, xz. And in fact, if you just have the side bisector of 2 of these, you know the third one also goes through there. And if I just gave you 2 chords, you have this a chord here, and if we took their side bisectors and their intersection, assuming these are not parallel, these two chords aren't parallel to each other, they uniquely define the circumcenter. So now what is this? Like, what are some, should I put this? What are interesting or cool bisectors we can take? Side bisectors we can take here. I invite you to take 5 minutes to figure that out. And for me, the very interesting one is to take the side bisector of A1, A2, and analogously for the other ones. And here's why. The reason why for me is this is 90, this is 90. So I know if I take the side bisector, it's going to be at a 90-degree angle. And if it intersects anything here, because all of these are parallel, right? The side bisector, call this point A4 the midpoint. We have A4N, A3O, A2H are all parallel to each other. And now you can have I think this is Thales' theorem, where this means that A2 over A4 is equal to A2 A4 over A4 A3 is equal to HN over NO. So that means that if you take the side bisector of A2 A3 and intersect it with HO, you'll get the midpoint of HO. Now, by analogy, if you do the same thing with B2 and B3, actually this is B2 and B1. If you do the same thing with B2 and B1, take their side bisector, intersect with OH, you'll also get N, which implies, well, it implies because these things are chords of the same circle, it implies N is the circumcenter of that circle. Now, what's an important point? I did not intersect these 2 side bisectors. If I did, I would have to prove an extra fact that they lie on HO. It will be a bit more difficult. Actually, I don't know how I would go about proving this, to be frank. I don't know how I would calculate this. To begin, like just right now, looking at it, I don't know how I would do it. But in geometry, the thing is sometimes you want to take advantage of symmetries. And you know that this A2A free thing, you know what the center is, right? You know this is here. So instead of taking a center and proving that it's here, you take that midpoint and prove it has to be the center, right? That's sort of the thinking. It's using a phantom point, as it's sometimes called. So with that, we've proved that this is the center. Now there's a lot of cool stuff going on here. Another cool fact that I'll mention here is A free, which is the center here. Because, mind you, all of these are on the same circumcircle, and this thing right here is 90. This means that A1, A free, passes through N. Because this is what is it called? The radius. This is the length of the radius. This is whatever. But now my question for you is, could you tell me how big is, so this has an interesting fact, which is that A1, A free, B1, B free, C1, and C free all pass through the same point, namely N. But there's also another interesting property. Can you tell me what the length of A1, A free is? And sort of express that in the elements of the triangle, like the side lengths A, B, C, or AO, AH. Could you do that? I invite you to take 5 minutes and think about, what is the length maybe of A free, A1? Take 5 minutes and think about it. And here's the cool thing. A free, A1 is equal to AO. Namely, the radius of the 9-point circle is twice as small, is actually, 2 times smaller than the radius of ABC. Now, that's a cool fact. And there are many ways to go about proving this. One way is, I'll go at it backwards and I'll motivate the next lemma I'll show you in geometry, is to say, wait a second, okay, if AO is equal to A1, A free, what do I have about these points? Well, I have this angle right here. I have what that angle is equal to. This is equal to beta minus gamma. I mean, the absolute difference of two. And this angle right here, it's equal to the angle that's on this sort of right here, chord here, A1, A2, which is equal to this thing right here, which when you calculate it, also ends up being beta minus gamma, which is equal to this thing right here. So we have A1, A free is parallel to AO and is equal to AO. That's what we would have actually, if it's equal. We know that it's parallel. We know that these two are parallel. And now we need to prove that they're equal, which means, but if they were equal, then this whole thing would be a parallelogram. But is it a parallelogram? And the answer is yeah. Why? Well, I invite you to take 2 minutes to figure that out. And here's the answer. A free, and OA1 are both perpendicular to BC. And because both of these are perpendicular to BC, that means they themselves are parallel to each other. So you have this is parallel to this is parallel to this, which means that A free, A1 is equal to AO. And this shows the thing I mentioned here. But there's also another interesting fact here. We have A free A is equal to OA1. And this thing right here is equal to a half of AH. So we have a relationship between AH and OA1, which is incidentally going to be the next lemma we are going to prove in a different way in the next video. in the next video on geometry. Now this solves our geometry, and this proves that these 9 points are on the same circle. The obtuse case, you might be wondering, now what about the obtuse case? What about the right-angled case? Well, if you have the right angle, then you have what? You have this thing, this thing. This is the orthocenter, this is the circumcenter. You have these 3 points, really. Many things collapse to each other. Actually, you have this point as well, this midpoint, and this midpoint. You have all these angles are 90. So it works out well. The obtuse case works similar to this. In fact, mind you, the obtuse case, it's like instead of ABC, you had HBC, right? Because this would be an obtuse case. And if you think about it, H becomes A, B2, so the B2 here would be still B2, C2 and A2 would all still be the same. Now, and the interesting part is like, the only thing that really changes in the obtuse case is now AC is really the midpoint between C and the orthocenter, like their midpoint. So B1 is like B3. So it ends up being just really the same thing. You've just renamed all the points. You know, take 5 minutes, you know, maybe think about this, but it's an interesting way to see like why you are immediately done in this case as well. So this solves our problem, and as always, thanks for problem solving.